Hello, I am Dr. Tatsuya Tanaka, neurosurgeon from Japan, and the first vice president of International League Against Epilepsy. Epilepsy affects up to 1% of the population, making it second to stroke as one of the most common serious neurologic disorders. In the past several years, our understanding of epilepsy has increased in several aspects. The first, advances in molecular genetics have revealed new syndromes and identified numerous hereditary patterns of epilepsies. The second, new and improved imaging technologies have documented subtle structural regions and provided structural function correlations. The third, experimental models have expanded the understanding of the mechanisms underlying seizures and epilepsy. Despite these advances and the availability of numerous new anti-epileptic drugs, our ability to eradicate seizures remains limited. Approximately 1/3 of patients still has uncontrolled seizures, and an even larger percentage suffers from treatment side effects of anti-epileptic drugs or from the psychological and social stigmata of epilepsy. Today, I will focus upon basic studies using experimental models of epilepsy and discuss about seizure propagation from the focus by way of seizure network. In the institution, seizure propagation mechanism and connectivity of the epileptic foci was studied by neurophysiological and metabolic approaches. At first, I want to discuss about complex partial seizures model. Here you have autoradiographic images of carbon-14 deoxyglucose during limbic seizure status in a rat. Elicited amygdala seizure propagate to the ipsilateral cortex, ipsilateral hippocampus, basal ganglia, and brainstem. Electroencephalographic and metabolic results were correlated in the schema. Focal limbic seizures propagate using anatomical pathways and subcortical structure connections. Here you have another radiographic images of carbon-14 deoxyglucose during canic acid-induced focal cortical seizures. Elicited seizures propagated not only to adjacent cortices by way of arcade fibers and fascicles, but also to the both subcortical structures and brainstem. In summary, advances in clinical and basic sciences are increasing our understanding of epilepsy mechanisms. In the present experimental study, seizures can easily propagate to the adjacent area, subcortical structures, and contralateral hemisphere. The mechanisms described today are by no means restricted to the level of the nervous system affected primarily. Our challenge is to find the true propagation mechanisms to understand pathophysiology in epilepsy and translate these into beneficial therapies of intractable epilepsy. Thank you for your attention.